So in the previous problems, when we were talking about sigma bonds and pi bonds, we started by talking about atomic orbitals, orbitals like an s orbital, or like a p orbital. P orbital. And these were areas where electrons, which zoom around the nucleus of an atom at over 4.5 million miles per hour, these are the sort of shapes that they blur into when they're flying around, depending on how much energy they have. So if it had a lower amount of energy, for example, an electron would blur into a sphere, twist a sphere, turn a sphere, it always looks the same. So there's only one s orbital an atom can have in an energy level. If the electron starts flying, getting a little bit more energy, just a little bit, then it starts flying around in this peanut shape. And when it flies around like that, it's a p orbital. Now, you can twist this and turn this so that it can either, instead of being vertical, it can be horizontal, or it can also be coming out at you and going away from you. So if you imagine, it would be sort of along that z-axis. So you have three different ways you could have those p orbitals. The thing with these orbitals, though, is they are only strictly true for hydrogen. For every atom except for hydrogen, they're only approximately true. They're only approximations. And the reason for that is because in hydrogen you have one proton and one electron going around it, and it's easy to track how that one thing is attracted to that one other thing. But even if you just had helium, you would have two protons, and so now your electron is attracted to both of those, which are in slightly different places, and this nucleus is constantly twirling around and so those two are changing their position. And in helium, there's another electron that's repelling that electron. So there's so much going on here that when you try to predict how this electron would move, you have to make simplifications. You basically would have to treat this like hydrogen in order to get these orbitals here for sure. So for every atom except for hydrogen, those atomic orbitals, s and p, are only approximations. And because they're only approximations for how the electrons are flying around those atoms, they sometimes lead us to a wrong prediction. And one place where they lead us to the wrong prediction is with molecular shapes. Now, there is a shorthand for what you can do to these orbitals to predict the correct molecular shapes. And this shorthand is going to involve mixing these orbitals. Mixed orbitals are called hybridized orbitals. Hybridized orbitals. So you could imagine taking your 1s orbital and taking all three of the p orbitals and throwing them into a pot and stirring it up, and what would come out of that cauldron, the new Frankenstein orbitals that you'd have, would look a little bit like a p, but they would have an enlarged lobe on one end because that's the end where the s orbital added. However many orbitals you added together, that's how many of these Frankenstein orbitals you'll get out, these hybridized orbitals that you'd get out. So you put in 4, you get out 4. And the name for these new Frankenstein orbitals, they're named after the orbitals that you mixed together to make them. So we mixed one s orbital with 3 p orbitals. And so the name for these new Frankenstein orbitals are sp3 orbitals. sp3 orbitals. So I'm going to move this over here. For sp3 orbitals, you mix the 1s with all 3 of the p's. You get these hybridized orbitals over here. And notice, I'm just going to make a very important note here. There are no p orbitals left over. Okay. So next, that's our first way of mixing these atomic orbitals. What's another way we could mix them? Well, we can take the s orbital and we can mix it with 2 p orbitals, 2 instead of 3. And again, we'd sort of get Frankenstein orbitals. They'd maybe be a little more stunted. They wouldn't be quite as long because not as much of them is p as before, only 2/3 rather than 3/4. However many orbitals you get in, that's how many orbitals you get out. And the name for these new Frankenstein orbitals, just like before, they're going to be named after the orbitals you mixed together. You mixed one s orbital with 2 of these p orbitals. And so the name for these are going to be sp2. The 2 is telling you how many p orbitals you mixed together. So these new, slightly more shorter and fatter orbitals, those are Frankenstein orbitals, those are sp2 orbitals. Now note, we only used 2 of the 3 p orbitals. And so I'm going to make a star down here and say there is 1 p orbital left over. And those p's, remember, look kind of like peanuts. Okay, that's our second way of mixing or hybridizing these orbitals. Last but not least, you could take an s orbital and you could combine it with just 1 p orbital. And if you put those into a boiling cauldron, however many orbitals you put in, that's how many we're going to get out. And the new Frankenstein orbitals here will be really short and fat because they're 50% s and 50% p. So as you mix fewer and fewer p orbitals into the s, the Frankenstein orbitals look a little bit more like s orbitals. And so these new Frankenstein orbitals are named after the things you mixed together. You mixed 1 s orbital with 1 p orbital, and so these are called sp orbitals. sp orbitals, because you mixed 1 s with 1 p. And notice, we only used 1 of the p orbitals. We still have we have 3 total to work with, so if we only used 1, that means that there are going to be 2 p orbitals left over or available. And so we'd have those 2 p orbitals. Okay, these are our 3 types of hybridized orbitals, the mixed orbitals that we're going to use as a shorthand to predict correct shapes. And so the key here are the p orbitals that you have. Remember that you need a p orbital in order to make a pi bond, that you couldn't make this pi bond with an s orbital. It's p orbitals that overlap in 2 places but have this interruption of the overlap in the middle. So however many pi bonds you have, that's how many p orbitals on an atom you need. So if you have no p orbitals, that means you can't form any pi bonds. And so you can recognize an sp3 hybridized atom because it will have all sigma bonds. Remember, those are the first bonds you ever form. You could recognize an sp2 orbital because if you mix them this way, you have 1 p orbital left over. You can recognize an sp2 hybridized atom because if you mix them this way, you'll have 1 p orbital left over. If 1 p orbital is left over, that means you can form 1 of these pi bonds. So you'll know you'll have sp2 if you have 1 pi bond. So an atom that only has 1 pi bond on it will be sp2 hybridized. For sp, this has two p orbitals. And if it has two p orbitals, that means it can participate in two pi bonds. So you'll recognize an sp hybridized atom because it will have two pi bonds. Okay, armed with this table, we can look at this problem here. And it says below are the structures of two common over-the-counter pain relievers. We've got aspirin. You can impress your friends by calling it acetyl salicylic acid. And we've got ibuprofen. So we've got those two, and what they want to know is the hybridization state of each carbon atom in these compounds. And what we're going to do is look at them one by one, each of the carbons, and ask ourselves, how many pi bonds do you have? How many sigma bonds and how many pi bonds? Now, so let's look at this carbon here first. The first bond you ever form between atoms is a sigma bond. So between these, you only have one bond, it's a sigma bond. Between here, you only have one bond, so a sigma bond. The first bond you ever form between atoms is a sigma bond, so that's a sigma bond. Every bond after the first bond is a pi bond, so that right there is a pi bond. So connected to this atom, we have only one pi bond. This second bond between the carbon and the oxygen there. And so, if you have only one pi bond, that is a sign that that carbon is sp2 hybridized. So this carbon here will be sp2 hybridized. Okay, let's look at the next carbon. This carbon here. The first bond you ever form is a sigma bond, so that bond is a sigma. This bond, the first bond between those carbons, is a sigma. The first bond you ever form between atoms is a sigma bond, so that's sigma. Every bond after the first bond is a pi bond, so this bond right here will be a pi bond. So around this carbon right here, we only have one pi bond. If you only have one pi bond, then you know that the hybridization of that atom is going to be sp2. So this carbon that's in this gray highlight right here will be sp2 hybridized. So this is sp2. Okay, next, this carbon here. So the first bond you ever form between atoms is a sigma bond, so that's a sigma bond. This is a sigma bond. The first bond you form between these carbons is a sigma bond, but every bond after that is a pi bond, so we have one pi bond here. And as we saw in the last two examples, if you have one pi bond, you are sp2 hybridized. So this carbon will be sp2 hybridized. If we go down to this carbon right here, we can see first bond you form is sigma. First bond you form between two atoms is sigma. First bond you form between two atoms is sigma. Every bond after that between two atoms is a pi bond. So we have one pi bond on this carbon. And so that carbon will also be sp2 hybridized. Whenever you have just one pi bond, it's sp2 hybridized, because if it's sp2 hybridized, that means you have only one p orbital left over. You mixed the other two with the s, and this p orbital that's left over can form the pi bond. Okay, so this right here, this carbon down here, is sp2 hybridized. And if we look at this next carbon right here, we will notice it very closely resembles the ones we've looked at so far. The first bond we form is sigma. The first bond you form between two atoms is sigma. The first bond you form between two atoms is sigma. Every bond after that first atom is a pi bond. We have one pi bond, And as we've seen many, many times, if you have one pi bond around an atom, that atom is sp2 hybridized. We can look at the next carbon. The first bond you form between two atoms is a sigma bond. First bond you form between two atoms is a sigma bond. First bond you form between two atoms, sigma. Every bond after that first bond is a pi bond. So here we only have one pi bond. If you have one pi bond, as we've seen in all of the other carbons so far, then that atom is sp2 hybridized. Okay, we're going to this one, last one in the ring. That one, first bond you ever form between two atoms is a sigma bond. First bond you form between two atoms, sigma bond. First bond you form between two atoms, sigma bond. Every bond after that between two atoms is a pi bond. So you only have one pi bond around this carbon here. One pi bond is there. And if you ever have only one pi bond, as we have seen on literally every carbon so far in this molecule, you've got an sp2 hybridized atom. So they only wanted the hybridization state of each carbon. So we're going to skip this oxygen. I'm going to look over here. All right, let's see how many sigma and pi bonds we've got there. First bond you form between two atoms is sigma. First bond you form here, sigma. Every bond after that first bond is going to be pi, so that's a pi bond. And so we have one pi bond around this carbon. If you ever have one pi bond, you know you only have one free p orbital. So the other two p orbitals mix with the s to give you an sp2 hybridized carbon. Last carbon in aspirin. So aspirin has a lot of these sp2 hybridized carbons. The last carbon in aspirin, let's see what we've got here. The first bond you form between two atoms is sigma. So these are all sigma bonds, a stronger type of bond with uninterrupted overlap between the orbitals, the atomic orbitals. So here we have all sigma bonds. Whoa, different case than from the other ones. If you have all sigma bonds, then the carbon is going to be sp3 hybridized. No, if all sigma bonds, then you don't need any of these p orbitals to make pi bonds. So this carbon in the top right, black sheep of the molecule, is going to be sp3 hybridized. And so that would be the hybridization state of each of the carbon in aspirin, or acetyl salicylic acid. Let's do the same thing for ibuprofen. Start at the left. Carbon. The first bond you form between two atoms is sigma. 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 Right? The first bond you form between any two atoms is a sigma bond. So that carbon has all sigma bonds around it. Well, we just saw if you have all sigma bonds, the carbon is going to be sp3 hybridized. So this carbon here will be sp3 hybridized. Okay, well, let's look at this next one here, this carbon. So we've got sigma, 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 so 4 sigma bonds. The first bond you form between any two atoms is a sigma bond. If you have all sigma bonds, then this will be sp3. Notice this carbon here, all sigma bonds around it. So that is also sp3. This carbon here, all sigma bonds. The first bond you form between two atoms is sigma, so that only has those single bonds, so that's sp3. Compare that with this carbon. The first bond you form between two atoms is a sigma bond. The first bond you form between these two carbons is sigma. Every bond after that, though, is a pi bond, so this right here would be a pi bond. If you have one pi bond, then you had to leave out one p orbital on the carbon to make that, which means you only had 2 p orbitals left to hybridize, so it's sp2. And we've seen that. We saw that a lot in aspirin. Anytime a carbon only has one pi bond, it's sp2 hybridized. And so you can see that all of these carbons in this ring are actually in that same scenario. Each of these has 3 sigma bonds around it. Oops, and let me also include this one. So like this one on the left has 3 sigma bonds and just this one pi bond. At the top, sigma, sigma, sigma. Every bond after that first bond is a pi bond. So each of these in this ring has just one pi bond around it, and if you ever have one pi bond, it's sp2 hybridized. So sp2, sp2. Just to drive it home one more time, you can see it. This one at the bottom right, the first bond you ever form is a sigma bond, so these are all sigma. Every bond after that is pi, so this right here will be a pi bond. So this carbon has one pi bond, and when you have one pi bond, you are sp2 hybridized. Notice the one pi bond here around that carbon makes that sp2 hybridized. All the others are sigma bonds. So that is sp2 hybridized. Okay, compare that with this carbon here. That carbon has first bond that you ever form between atoms is sigma, so these are all sigma bonds. And if you have all sigma bonds, and you don't need any p orbitals left over, you can mix all 3 of the p orbitals with the s orbital and get sp3. This carbon here, sigma, 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 all sigma bonds leaves you with an sp3 hybridized carbon. And finally, that carbon there, the first bond you form is a sigma bond between any 2 atoms. Those are all sigma bonds. Every bond after that, first bond is a pi bond, so we've got just this one pi bond on that carbon. When you have one pi bond, the carbon is sp3 hybridized. And so you can identify the hybridized orbitals on carbons based on the number of sigma and pi bonds that they have. If you have all sigma bonds, it's sp3. If you have one pi bond, it's sp2. And if you have 2 pi bonds, it would be sp3.